Right. So here, the idea of pipelining is very simple. I'm going just to show it here to the real world. So assume that we have 3 stages. Okay, now we have these 3 stages are like 3 resources. So I have a washing machine, I have a dryer, and I have myself. I have myself as a 3rd resource. Now the question is here is suppose that if, let us say on a weekend you would like to go and do your laundry. I don't know if you have done it yourself. Okay, if you do your laundry, so what you have to do is that you have to take your laundry, okay, and you have to wash, you have to dry, and you have to fold. Okay, so suppose that we have 4. Okay, in this simple example, I would like to use here 4 loads of clothes here, which are shown here. Okay, A, B, C, D. So each one I would like to wash, dry, and fold. Right. So if I would like to do it sequential laundry, this is an example from the real world just to compare sequential execution versus pipeline execution. So if I would like to do it sequentially, we start here on a weekend at 6 p.m. Then I'm going to start with load A. I will wash, it will take 30 minutes. Then I will dry another 30 minutes, plus 30 minutes actually to fold. Then I will start B at 7:30. I will finish at 9. Then C, I will start here at 9 p.m. I will finish at 10:30. And then, okay, I will start D at 10:30 and I will finish by 12 midnight. Okay, so the total execution time is 6 hours for 4 loads. Very simple. Okay, so it takes 6 hours because it takes 90 minutes. Okay, to wash, to dry, and to fold, multiplied by 4 loads. So this took actually 6 hours. Let us actually do better than this. Now, intuitively, we can use pipelining. I don't know if you have done it. Okay. So how can we do it with pipelining? Anyone?
We will use more than machines at the same time.
No, the same machines. Same machines.
Yani after the first 30 seconds, the washer is empty, we can use it again.
Yes. So what we need to do is that we can overlap the use of these three resources. Yani once we finish the washing of load A, we don't really have to wait for drying and folding it to start B. Yani the washing machine is empty, right?
Yes.
To start the load as soon as possible. That's really the idea. So we have 3 resources. I have the washing machine, I have the dryer, and I have myself. So again, we start load A at 6 p.m. It takes 30 minutes. Okay, 30 minutes to finish load A. Now at 6:30, now the washing machine has completed. We can take the load from the washing machine into the dryer, but the washing machine is empty. So I can start load B on the washing machine. Okay, that's really the idea of pipelining. So I can start B as soon as possible. You don't really have to wait for A to complete because B is not related to A and the washing machine is empty. That's really the idea of pipelining. And then at 7 p.m., okay, B has finished on the washing machine, A has finished on the dryer. Now, what I need to do is that I need actually to empty the dryer. So I can take out, okay, the load A from the dryer. So the dryer will be empty. I can move B into the dryer, from the washing machine into the dryer. I can start C on the washing machine. And during these 30 minutes, I'm using C on the washing machine. I'm using actually B. I'm going to dry B. And I'm going to fold A. So I can fold them. I can actually iron them, whatever. Okay. So, so that actually can be done. 3 things can be done in parallel. If you continue like this, you can finish at 9 p.m. So therefore, we have reduced the total execution time from 6 hours to 3 hours. And therefore, we have achieved a speed up. And the speed up factor is equal to 2. Because if you divide 6 hours by 3 hours, you get the speed up factor equal to 2. So definitely pipelining is much better than the serial execution. Okay?
Yes.
Now notice that the time to wash, dry, and to fold is still the same. We did not really change anything. It takes still 90 minutes to wash, to dry, and to fold. We did not really change that. what we did is that we tried to use these three resources in parallel at the same time. So we overlapped, okay, the use of the washer, the washing machine, the dryer, and the use of the human resource. Okay, so these three things are operating in parallel rather than waiting for the complete load A to complete and then to start, okay, load B. This is exactly the same thing in the case inside the CPU. Now, remember, in the case of the multi-cycle, we divided, we broke down, okay, the instruction into multiple steps. So why should we wait until the instruction has completed to start a new instruction, like in the case of the multi-cycle? We can do a lot better by pipelining, and we can achieve much higher speed up by using pipelining over the multi-cycle implementation. So multi-cycle is better than the single cycle, but we can do better than the multi-cycle by using pipelining. So the idea is to break down a task into k subtasks. Okay, that's really the idea. And we can execute these k subtasks on k different stages of the pipeline. And each subtask requires one time unit, for example, 1 clock cycle in our example, in the case of the CPU. And the total execution time of the task is k time units. Yani to go through these k stages, it takes k time units. So the idea of pipelining is to overlap the execution. Yani we don't really wait for one task to complete to start another task. So if I would like to have the execution, if I would like to have serial execution, which is shown here. So notice that without pipelining, what we do is that we complete one task that consists of k subtasks before starting the second task. Okay, so that's called serial execution. So you complete one instruction before you start fetching the next instruction in memory. So this is without pipelining. So the idea of pipelining is that since we are breaking down, okay, the task into k subtasks, once the task goes from stage 1 to stage 2, we can start fetching the next instruction, or we can start the next task on stage number 1. And when the task goes from 2 to 3, so this is will be 3, then the second one will go into stage 2, and we can actually start a new task in stage number 1. So this is really the idea of pipelining. Now, if you look here without pipelining, you can see that there is one completion, one task completed. So one completion here every k time units. So it takes k time units to complete one task. However, if you use pipelining, you can have one completion every 1 time unit. So after finishing the first task, then it takes only 1 time unit to finish the second task, and it takes 1 time unit to finish the next task, and so on, the third task, and so on. So you have one completion every 1 time unit, and this is how we can improve the performance. Okay, so the pipelining, the idea of pipelining is to improve performance. So by the way, people have discovered pipelining since the early days of computing, or even before that. People in the industry have been used pipelining. For example, if you look at the auto industry, there is always some kind of a pipeline. Okay, or in any industry, there is something which is called the assembly line. So the idea of the assembly line is to have pipelining. Okay, so you don't really have to complete the task to start a new task, and basically you can overlap them. By moving the task from one stage to another stage, you can start a new task. So that's really the idea of pipelining, but we're going to apply it in the case of the CPU design, and we're going to implement the data path and the control to be pipelined. Okay, questions? I don't know if there's a comment here. Type. Can you all join? I mean, there is a comment here this morning. Can you all join? Do you have a problem with joining MS Teams?
I don't.
I don't.
Okay, all right. So, let us. Do you have any question about the concept of pipelining? So we have seen pipelining as a simple example last time, which is related to laundry example. Okay, that was a simple example. So even as a human beings, okay, we can try to improve, reduce the execution time. When we have, let us say, many loads of laundry, we don't really have to finish one load to start another one if you have multiple resources. So we have the washing machine, we have the dryer, and we have ourselves. We have a human resource that can fold and put the clothes into cabinet. So you see, we can actually improve. We can reduce the execution time using pipeline. Right. So let us go slightly into more details. Now, how do we implement a pipeline, a synchronous pipeline, okay, in the hardware? How do I design a circuit to be pipelined? This is the question. Now, the answer is simple. Okay, it is shown in this slide. And the idea is to introduce registers between the different stages. So if you have a circuit, you can break down this circuit into multiple stages. So here the stages are called S1, S2, Sk. I'm showing the stages here in yellow. These are the stages of the pipeline. So we have K stages. So K depends, of course, what you are trying to do in this circuit. So if you can break down this circuit into K stages, you can introduce a register. Okay, so what you need is that you need to introduce registers. So these registers are clocked. So notice that there is a register between every two stages. So at the end of each stage, there is a register. There is also a register at the input of stage S1. So basically, the first register is going to receive some input. And then the last stage is going to produce the final output. For example, if you have a pipeline functional unit or execution unit, and let us say it will take multiple cycles to execute, you can break it down into multiple stages, and you can introduce a register at the output of each stage. So this way, you have a pipeline. Okay. Now notice that all of these registers are clocked. Notice the clock is connected. Okay, so it is used to synchronize the operation of the pipeline, and it is connected at the clock input of all these registers. So at the same edge of the clock, all of these registers are going to update their state or their values. So therefore, the registers will update at the same edge of the clock, and you see that the output of S1, okay, will be stored inside the register at its output. The output of stage 2 will be also stored, okay, in the next register, and so on. And the output of the last stage will be stored in the last register. So all of them will update at the same moment in time, at the same edge of the clock. Now, it is very much, so these stages are nothing but combinational logic. And in between, we are actually storing, we are putting registers that will store the results of these stages, of these combinational logic circuits, okay? Now, because we are using a clock here, okay, to synchronize the operation of the pipeline, it is very much desirable to have these stages to be balanced. In other words, the meaning here of balanced stages, it means that we would like to have almost, okay, the same delay, approximately equal delays in all stages. Now, we cannot guarantee that, but we try to reduce the delay, okay, so that we can balance, okay, the delay in these stages. Yani we don't really want to have one stage taking too long and another stage to be too short. Okay, so balancing the delays in these stages is very important. Otherwise, this is going to impact the performance of the pipeline. Now, how do we determine the clock cycle or the clock period? We look at the maximum stage delay. So we look at the delay in S1, we look at the delay in S2, we also look at the delay in the last stage, in all these stages, and we go by the maximum stage delay. That's how we determine, okay, the clock cycle or the clock period. So the maximum stage delay is going to define the clock cycle. because during the same cycle, okay, all of these stages are going to be used at the same time. So the one that has the longest delay is going to impact the clock cycle. Okay, students, do you have any question about this? Right. So I will later show you how we can implement the MIPS pipeline, but this is basically the idea behind implementing a pipeline. Now let us take a look at the performance of the pipeline. Okay, suppose that we define here T sub I or tau sub I. So tau is like T, but a Greek letter. So this is the time delay in a stage S sub I. So we have seen in the previous slide, we have seen K stages. So each stage will have its own delay. Now we can define the clock cycle here to be maximum T sub I. Okay, that's the maximum stage delay. Okay. Now notice that when I talk here about the stage delay, what I mean here, okay, from the previous slide, not only the delay in the combinational logic, but also there is a setup time for the register, and there is also a delay to change the output of a register from the clock edge until we get the output. So also the register delay has to be added, okay, to the delay of these stages. Okay, so that's how we define here, okay, the tau sub I. So we take into account also the delay in the registers. Right, so we can look here at the maximum stage delay, which is tau, which is the maximum tau sub I, and this will define, okay, the clock cycle. If I would like to find the clock frequency, so the clock frequency F is just 1 over tau, which is 1 divided by the maximum tau sub I. Right. If I would like to look here at the difference between, okay, let us take a look at this slide. If you have n tasks or n instructions, okay, so here my task is the instruction, and we have k stages in the pipeline. If I don't use pipelining, if I use serial execution, okay, and you have n of these tasks, and each one has to go through k stages, okay? So what will be the duration? And suppose that each stage will take 1 cycle. Okay, so here the time unit is just 1 cycle. So how many cycles does it take to execute these k? So if I would like to execute n tasks, okay, without pipelining, how long does it take to execute?
N times k.
Exactly, it is n times k. And if I would like to use here my pen tool, so this will take here n. So let me write here n, capital N, multiplied by, so we have to multiply it by k. Okay, I'm writing with my mouse. Maybe I need actually to use a pen tool. Type. How about if I would like to do it with pipelining? How long does it take to execute n of these tasks on a k-stage pipeline? If I would like to do it here with pipelining.
Tau max. Sorry.
No, forget about the clock cycle itself. Forget about tau. Let us just count the cycles. So here we counted n, which is the number of instructions, multiplied by k cycles. Okay.
So
forget the delay. Okay, the clock cycle itself. So we're just counting the cycles here. So it's n times k cycles. Here, how many cycles?
N times.
Let's count them properly. Now the first one will take k cycles to complete, but the second one will take how many cycles?
N minus 1.
Well, if I finish here, so k to complete the first one, right?
Yes.
But to complete the second one,
we need only k.
No, we need only 1 extra cycle.
Yeah.
So if you have actually if you have only 2 instructions, it would take k plus 1.
So it will be k plus n?
It will be k plus n minus 1. So k for the first one, and 1 cycle for each of the remaining ones. So if I would like to write it with my pen tool, where is my pen tool? Maybe it's not here. Anyways, with my mouse. So it is k. Okay, that's k. Just give me 1 second. Give me 1 second. I'll be back. Type. So again, let me try to write it in a better way. Okay, so in the case of pipelining, it takes k cycles, okay, to complete the first task clearly, right? So it's k plus, if we have n of these, it will be plus n minus 1. Do you agree? So that's the number of cycles with pipelining. So if you have, for example, n is equal to 2, it will be k plus 1. If you have just one task, it will take k. If you have 2, it will take k plus 1. If you have 3, it is going to take k plus 2. If you have n, it will take k plus n minus 1. Correct?
Yes.
Okay, so that actually is from this diagram, it's very clear. Right. So that's actually with pipelining. So now if I would like to find out the speed up of pipelining. So the speed up of pipelining, we divide the serial execution time in clock cycles divided by the pipeline execution time in cycles. So the serial execution time will be n multiplied by k, that's serial execution. And the pipeline execution, so n multiplied by k, and here is the number of tasks or the number of instructions. So remember that task here means an instruction, okay? In fact, it can be applied to anything, any pipeline. We're talking here about the CPU design, but really we can also apply it in the auto industry. So the task can be a car, okay? And of course, the car has to go through hundreds of stages to complete. Okay, so we can also use pipelining in the case of the car manufacturer. Okay, he wants to manufacture, let us say, cars. Okay, starting with an empty body and then putting the engine, putting the glass, putting the wiring, putting the whatever. Okay, painting. Okay, so all of these are done by robots today, not by human beings, but that's also is a pipeline. Okay, it's a pipeline. So if you use serial execution, you have to complete one task before starting the next one, and each has to go through k stages. So it's n multiplied by k. That's the serial execution. If you look at pipeline execution, it will be k plus n minus 1, as we have seen in the previous slide. Okay. Now, typically, in the case of a CPU execution, n here is the number of instructions, and k is the number of stages. So that's actually SK, that's the speed up on a K stage pipeline. Okay, so now because we have N is the number of instructions, and typically in a program you have billions of instructions. Okay, and these billions of instructions can take actually sometimes a second or even a fraction of a second. So, so therefore this N here is much, much larger than K. Okay. So if, for example, if n is like 1 billion and you have a 5-stage pipeline, you can see that here n is much greater than k or k minus 1. So we can approximately, if n is very large, for large n, if n is very large, okay, that's typically the case when you are executing instructions inside the CPU. We can approximate this. Let me write it down here. So this is approximately is equal to what? K plus n minus 1 is approximately equal to what?
K plus n. Yeah, okay.
N. So we say that in the limit, mathematically, in the limit as n goes to infinity, remember mathematics?
Yes.
The limit, okay, so as n grows We don't really have to take it to infinity. We can just make it large. And K is the number of stages in the pipeline. So typically this number of stages is typically small number of stages. You don't really have actually like hundreds or thousands of stages. No, you only have few stages in the pipeline. N can grow. N can become billions of instructions in a given program. So we can say if you have, let us say, very large N, then N plus K minus 1 becomes approximately equal to N. Right?
Yes.
So now we can say, let me put it differently. Okay, you know that people actually, people who are billionaires, right? They have actually billions of reals.
Yes.
Yes. Okay. So if you have 1 billion real and you add to it actually 1 billion plus, let us say, 5 reals, does it matter actually if you have 5 extra reals or not? So when you put actually 5 reals in comparison to 1 billion, you can ignore the 5, right? If I have in my pocket 1 billion, do I really care about the 5?
No, I will not care about
That's
5.
the same thing here. That's actually is the same thing. So you have actually here, if you have actually N very large, do you care about the K minus 1? No, you can approximate, okay, N plus K minus 1 to be approximately equal to 1. That's really the idea behind it, okay? I just put it in the case of money. So now we can say that, okay, we can divide here NK divided by N, and this is approximately equal to 2. Now that's expected. You get the speed up of a K stage pipeline to be approximately equal to K for large N, which means that you have K stages that are operating in parallel. Okay, so the speed up S sub K will be approximately equal to K for large N. And the reason why it's approximately equal to K is that you have K stages that operate in parallel. So we expect the speed up to reach K for large N. Okay, so this is what we call the ideal speed up. Okay, so that's the ideal speed up. And that's the ideal speed up, okay, over serial execution when you compare it with serial execution. Right, let us take a look at this example. Now, before I show you this example, okay, in the case of the MIPS processor, we are going to design also a pipeline. And this pipeline will have 5 stages because it's a simple CPU. The first stage will be called the instruction fetch stage. So that's IF here, instruction fetch. The second stage is called the instruction decode stage. That's instruction decode. Okay. So during the stage, we use the control logic to decode the instruction to generate all the control signals. And then also we can read from the register file, and also we can calculate the jump and the branch target address. So all of this can be done during the same stage. Okay, so these 3 things can be done in parallel because they are not related. And the third stage, which is called the execute stage, we execute the instruction. But if the instruction was load or store, we can use this execute stage to calculate the load store address. And the fourth stage is called the memory stage. We use it to access the memory. That's the memory access stage for load and for store. And the last stage is called the write back stage. This is when we write back the result into the destination register. Okay, so these are the 5 stages of the pipeline. Now, this is a very simple pipeline, but it illustrates the concept of having overlapped, okay, the concept of pipelining or the overlapped execution of instructions. So we only have 5 stages. Typically today, if you look at the real processors, you might actually have, depending on the CPU, you might easily have like 10 stages or 15 stages in the pipeline. So the pipeline is deeper than this, okay, in real CPUs today, which are produced by different companies, let us say ARM or Intel or AMD, we'll find that the pipeline actually can be deeper than this. So this is just a very simple 5-stage pipeline. Here's actually an example about performance. Yes, Omar?
So only the first 2 could be done in parallel since they are independent of each other?
No, all of these 5 can be done, actually can be done in parallel on 5 different instructions in the pipeline.
Oh, I see.
But what I meant is that within a stage, you can do multiple things. Yani, for example, in the second stage, in stage number 2 here, which is the instruction decode, you can decode the instruction to generate the control signals. You can read from the register file. This can also be done during the same stage. Okay. You can also calculate the jump and the branch target address. Now, if you cannot do all of these things during the same stage, then you can split them into 2 stages. But in the case of our simple MIPS processor, I can do these 3 things in parallel during the same stage. So I can do more than one thing during the same stage. Otherwise, if it cannot be done, then I have to split, okay, the stage into multiple stages. But for our case, it can be done. Okay, so we can just put them in the same stage. But all of these 5 stages can be, okay, operate in parallel, okay, can be used in parallel on 5 different instructions in the program. So once we have filled the pipeline, we can see instructions are actually writing back, so we can complete 1 instruction every cycle. Right. Let us take a look here at a simple performance example before I go into the details of how we can implement the data path and control. So this is an example about single cycle versus pipeline performance. So here we have a 5-stage instruction execution pipeline, okay, what we have seen in the previous slide. And it says that instruction fetch and ALU execution and data memory access are 200 picoseconds. So we can do this in 200 picoseconds, whereas register read and register write are 150 picoseconds. So to read or to write into the register file, it takes less time. Right. So the question is, what is the clock cycle if I would like to implement this as a single cycle CPU? If I would like to implement this also as a pipeline CPU, what will be the clock cycle? And what is the speed up factor of pipeline execution over the serial execution, over the single cycle CPU? So how do we answer these questions? Anyone?
Yes. First question is 750. The second,
so
200.
How did you calculate this?
Just because the steps we have to go in series to execute.
So what are you adding?
So 200 plus 200 plus 200 plus 150. Yes, plus 150 for the register read or write.
Well, we are going to do
750.
We are going to read and we are going to write.
Yes.
So it's plus 150 plus another 150.
Sorry. Okay. So it's 800. It's 900.
Yes. Now for the single cycle clock is going to be 200 to fetch, 150 to read from the register file, 200, okay, to execute, 200 to access the data memory in the case of a load instruction, because we have to go by the slowest instruction in the instruction set. And we need actually 150 to write the data back into the register file. So this will take 900 picoseconds. Okay, do you agree? That's the clock cycle.
Yes.
That's the minimum clock cycle for the single cycle clock. Of course, we can increase it, okay, to have actually small margin, and we can increase, but that's actually the slowest. Okay, that will be this. This is as a minimum. We need 900 picoseconds. Okay, we cannot reduce it below that because we have to take into account the delay of the longest instruction in the data path. Okay, so that will be 900 picoseconds. And this is shown here. This is the single cycle. This is the single cycle processor. So notice that we have to do all of this. We have to fetch, read from the register file. So this is the instruction decode stage. And we read also from the register file. This is the execute stage. This is the memory stage in the case of load and store. And this is also the write back stage, to write back to the register file. So we have to finish one instruction before start to fetch the next instruction. So there is no serial execution here. Sorry, there's no pipeline execution. This is pure serial execution. Okay. So this is serial, not pipeline. Now let us take a look at the pipeline clock cycle. What will be the pipeline cycle?
200.
Yes. So how did you calculate this?
Tau I, the longest delay in one step or one stage.
Yes. So we have to go by the longest delay at any stage. So we have some stages will take 200 picosecond, and we have other stages that will take 150. So here we go by the maximum, which is 200 picoseconds. Okay. Right. So that actually is good. You can see that the clock cycle is much better. Now the question is, this is basically it. Okay. So you can see that this is actually pipeline execution. It takes actually 200 picosecond to fetch. After we fetch, we decode the instruction and we read from the register file. Now notice that we have fixed the clock cycle to 200 picosecond, even though it takes slightly less to read from the register file. In the second stage, it takes only 150. But even if it takes 150, we're going to actually fix the clock because we cannot change the clock. Okay, خلاص, we fix the clock frequency. And therefore, the clock cycle will be 200 picoseconds, even though this will finish early. That's fine. That's fine. So we always go by the maximum delay at any stage. So the maximum delay here is 200 picoseconds. Okay. And therefore, this is actually this pipeline execution. So we fetch one instruction every cycle we fetch. Okay, even before the instruction completes. All right, so the question is, what's the CPI? What's the CPI for pipeline execution? What? What's the CPI? Okay, let me ask you a different question. What's the CPI for the single cycle CPU?
1.
Yes. What's the CPI for the pipeline processor?
It is different for each class, and we need to calculate the weighted average to find the CPI for pipeline.
No, that will be for the multi-cycle. We did that for the multi-cycle. So for the multi-cycle, we had the CPI changing from one class to another class. That was for the multi-cycle implementation. But for the pipeline processor, what's the CPI? Well, you cannot see it. Amr?
Yes, I wanted to say 5.
5?
Not
That will
5.
be
Sorry, 0.2.
0.2?
Because we have 5 cycle per instruction. Isn't that correct?
Okay, no. This is not how we calculate the average CPI. Ali, can you answer this question? Can anyone answer this question? Ali, تفضل.
I think it's fixed.
طيب. Okay. Let us say that, okay, let me ask you the question differently. At what rate can we complete instructions?
200,
at what rate?
200 per the number of
forget about the clock cycle time. Yes, the clock cycle is 200 picoseconds, but the question is, at what rate can we complete instructions? Can I complete one instruction every cycle? Can I finish one instruction per cycle?
I can finish one instruction every 200 picoseconds.
Okay, well, 200 picoseconds is the cycle.
So I have 200 over m, which
so
is
the cycle is 200 picoseconds. So the cycle is 200 picoseconds. So therefore, I can complete one instruction every cycle. So after we have finished the first instruction, notice that it writes its result into the register file. We can complete the next one. We can complete the next one. We can complete the next one. So one instruction completed every cycle. Forget the time to fill the pipeline.
One.
Initially, because we have a large number of instructions in our program, forget the time to fill the pipeline. So once we have filled the pipeline with instructions, if you look at the last stage of the pipeline, Just focus on the last stage. If you focus on the last stage, you can see the program completing one instruction every cycle. You finish one, then you finish the next one. Every cycle you can complete one. So the CPI for pipeline execution is also 1. We ignore the time to fill the pipeline because it takes actually several cycles to fill the pipeline. But once we have filled the pipeline, you can complete one instruction completing each cycle. Okay, so each cycle we can complete one instruction. So therefore, that's actually is the CPI. The CPI will be one instruction per cycle. Of course, we have to ignore the time to fill the pipeline. So that's actually is the CPI. So since we are fetching one instruction per cycle, we are also completing one instruction per cycle. So we are reducing the CPI to just 1, regardless of the class of the instruction, regardless of the type of the instruction. So even though some instructions would take less or take longer, it is just one instruction each cycle. Because we are fetching one, we are completing one each cycle. So that's the rate at which we are improving the. So the CPI is just the same thing as the CPI for the single cycle, except that the clock cycle is much shorter. So now we can say that the speed up of pipeline execution. We can look here at the serial execution time, and we can look at the pipeline execution time. The instruction count is the same, so it does not really. So we don't really have to show the instruction count. We multiply it by the average CPI, which is 1. We multiply it in the case of the single cycle, and it's also 1 in the case of the pipeline. So the CPI is the same, 1. And we have here the clock cycle divided by the clock cycle. So the clock cycle was 900 picoseconds in the case of the single cycle, and it's only 200 picoseconds. So we achieved here a speed up of 4.5. Okay, so 4.5x faster. Okay, that will be the pipeline CPU over the single cycle CPU. Much better speed up than the multi-cycle CPU. In the case of multi-cycle, we achieved also a small speed up, like 1.17. I forgot the exact number that we have seen it in a previous example, but that was actually a small speed up. But in the case of pipeline, we can achieve much better speed up. Okay, so 4.5x here indicating that it's more than 4.5 times faster, okay, than the single cycle CPU. Okay, so you can see that the instruction count and the CPI are equal in both cases, in the case of the single cycle as well as in the pipeline. Right.
Doctor,
what is the yes, Ali,
4.5 speed up for just a MIPS pipeline processor?
For using pipelining, yes. For using pipelining over the single cycle. Okay.
For the MIPS.
Yes, we are talking about this 5-stage pipeline, this specific 5-stage pipeline.
Okay.
If you change the design, you might actually achieve a different. Yeah. Okay, if the number of stages changes, you can actually achieve maybe a different speed up. Fine. So now the question is, what's the ideal speed up? If you have a 5-stage pipeline, what's the ideal speed up?
5.
Yes.
5.
The ideal speed up should be 5 because we have 5-stage pipeline. But we did not achieve 5, we achieved 4.5. So we did not really reach the ideal speed up, which is 5. Why did we not really reach the 5?
Waiting for the pipeline to fill.
Well, not because of this, no.
Because not all instructions have the same cycle.
It's because it's not like that. It's because
sorry, not instructions, I mean stages.
The stages, they are not balanced, right? So we can see that the stages, some will take 200 picoseconds, another one will take 150 picoseconds. So in the case of the single cycle, notice that we got 900 picoseconds. Why? because some stages took actually less than 200 to 150. So we took advantage of this in the case of the single cycle to reduce the clock cycle for the single cycle. It was 900. But in the case of the pipelining, it was 200 because we have to go by the maximum delay at any stage. So because the stages are not really perfectly balanced, so we did not really reach here the ideal speed up of 5. So the speed up factor is less than 5, which is the number of pipeline stages. And the reason is that because the pipeline stages are not balanced. Okay. So this is my example about single cycle versus pipelining. So in summary, pipelining does not improve the latency of a single instruction. It does not improve latency. And the reason why it does not really improve the latency because the instruction still has to be fetched, has to be decoded, has to be executed. Sometimes it has to access the data memory, okay, in the case of load or store, and it has the result, okay, has to be written back into the register file. So the latency is still the same. In fact, the latency can be worse in the case of pipelining because we have introduced pipeline registers, and these pipeline registers are going to slightly increase the delay. Okay, so the latency will be slightly increased in the case of pipelining. So pipelining does not improve the latency. You still actually have to do the same thing in the case of pipelining. What we are improving is the throughput. It means the rate at which we can complete instructions. So what we are improving is the clock cycle. We are reducing the clock cycle. We are using a much faster clock. So you can see that the instructions are initiated. So we fetch them and we complete them at a higher rate. So this higher rate comes from a higher frequency for the clock. So if you have a k-stage pipeline, we have k stages are operating in parallel. So you can have k instructions in the pipeline at the same time. At any given cycle, you have k instructions in the k different stages in parallel. That's actually what you can achieve with pipeline. So because we have this kind of overlapping between these multiple hardware resources, we have multiple stages. The potential speed up is the number of pipeline stages. That's the potential speed up. This should give you the ideal speed up, should give you k. The problem is that, okay, if the stages are not really balanced, we have to go by the slowest pipeline stage. And this is going to limit the pipeline rate or the pipeline frequency, the clock frequency. Okay, so it depends on the slowest stage in the pipeline. So if these stages are not really balanced, this is going to reduce the speed up. Okay, so if these are unbalanced, okay, then the speed up will be, well, this is going to impact the performance and the speed up, as we have seen. Also, the time to fill and drain the pipeline, I did not talk about it. So if you empty the pipeline and then you fill it, this is going to also to impact reduce the speed up. But I will talk more about it in my next presentation.